the multitask learning problem. Okay, so we want to learn and effectively fine-tunable model, okay, for new tasks. So this changes our perspective, right? Instead of thinking about we have a lot of data for the task that we want, we'll train a model from scratch. Instead, we take the perspective of we're going to build potentially a bigger model that we want to be able to fine-tune for the tasks we want. And implicitly, the mammal picture, so parenthetically, implicitly, for mammal, want to be able to fine-tune using small amounts of data. Task-specific data. So this is the objective. Then how do you even formalize this as a kind of problem given what your data? So the idea is we're given a training data set of data sets. So instead of having a data set tied to a particular task, you have a data set of data sets tied to many different tasks. Right, so you have task I, example J. So we have this data set of data sets, which is our training set. Right? We want to learn/train a model. And so the mammal perspective, which I was describing last time, but then we ran out of time, was to treat this problem as you can think of it as like a baseline approach. Treat this problem the same way we would treat a standard learning problem, a standard supervised learning problem, which is to do SGD. So what does it mean to do SGD on this problem? Quote, do SGD. So you think back, the idea of SGD is we take a particular example and we see how we do on it. Having seen how we do on it, we also compute gradients for what our model would have been that would have made it better, and then we take a step in that direction. Remember? That's how SGD works. So we want to take that same idea and apply it here. And so the key insight is that from the perspective of SGD, when you pick, quote, one thing, the thing you're going to pick is a task, not an example for a task. Do you see that? Because the thing you want to do well is to generalize across tasks. Okay, so key idea. Treat a task as the elementary thing. Now we'll have to adjust this, but that's the idea. So how do we do this? Like how does this actually turn into something to do? So there's going to be many, many things we're going to have to work out. So let's start with the most simple thing we could try, and then we'll adjust from there. Okay? So one thing you could do is to say, so idea 0, or idea 1 maybe, or approach 1. So we're going to do in a few steps. First step, we're going to randomly pick. So I'm not even going to talk about, we're going to randomly initialize our network. Okay, whatever, we did that already. Maybe we started with a pre-trained network for some other self-supervised task. That's just, consider that done. So we randomly pick a task. Okay, so this is a task I. Okay, so we randomly picked a task I. Now, we want to do the SGD style of we want to see how well do we do on this task. And then we want to compute a gradient. Okay? So the second step is to say, how well do we do on the task? So how do we tell how well we do on the task? Well, what are we going to be doing in this problem? What we're going to be doing in this problem is, what we want to be able to do is to fine-tune. So the first thing we have to do is actually fine-tune. Okay, so we fine-tune. Our model using training data, xij, yij. So this involves lots of choices, which I'm just going to consider built in. Like this is choosing a loss function, choosing a way of making gradients. You have to choose lots of choices in here, so just make a comment here. Choose a loss, relevant to task. If the task is such that it really needs to have, you believe, a task-specific head initialized, then also that comes in here, initialize the head. Like all that comes in to choose a loss, choose a learning rate. These are all design considerations that are done by a human or by automatic hyperparameter tuning. Choose a learning rate, etc. All that stuff. Now, we have to see how well do we do, right? To be able to take an SGD step, we have to be able to see how well do we do. So simply training it doesn't tell us how well do we do. So how do we tell how well do we do? Anyone? How can we tell how well do we do on this task? We have to use a test set, right? So we have to hold out a set. So we have to fine-tune our model using training data. Okay, so that involves here do a train test split. Okay. So we fine-tune our model using a training test data, using training data. Training data, and evaluate on held out training test data. So we do the usual evaluation on the training test data. So to be specific, we have to choose a training loss relevant to the task. We have to choose test loss relevant to task. Okay, so now we've evaluated the model, which is now being fine-tuned on this training data, and we evaluated on the held out test data. So now we need to compute a gradient. Okay, so this involves we have to compute a gradient to something. So C, I'll just write it, ask PyTorch to compute a gradient. But the question becomes a gradient to what? Right? You can ask PyTorch to compute lots of different gradients. So it's a gradient first to what and of what. So the gradient of what we know, it's going to be the test performance, because that's how well we do on the task, right? So gradient of training test performance. Okay, so that's the thing we're going to compute the derivative of, but with respect to what? So when you compute derivatives with respect to something, the thing you compute them with respect to is what you're going to be taking an update step on, right? Okay, that's the point of the gradient, is to allow you to do gradient descent. So we have to ask ourselves, what do we want? What are we trying to get? What we're trying to do is to learn a fine-tunable model. So we need to take a gradient step on the thing that defines the fine-tunable model, because that's our goal. So when you have to take the gradient step with respect to the thing you fine-tuned. So these are your model parameters before you did step B. So think of it this way. You randomly picked a task. You look at your model parameters for your model that you're going to fine-tune. You then run a bunch of training steps on it to update those parameters to something. Then you use those now fixed parameters to evaluate yourself on a test set to get a loss. And then you ask, what is the derivative of that final loss with respect to where you started in training? Okay? And then do an update on that. So last part, D, do an update. Okay, so at this point, what I want to make sure everyone understands is two things. First, explicitly what we're talking about, what we're saying here. Like, at this point, you should be able to write PyTorch code to do this. So if you have any questions on how you would do this, you should ask. Second, you should understand how this is a manifestation of the idea of doing SGD, except where training examples have turned into entire tasks. Okay? But then we're going to talk about like more details of how this is done and kind of complications and things like this. But you need to understand the big picture. So, questions on this? So I'll draw a little picture. So, mammal. So this isn't the homework. You'll have to do it all explicitly in a very concrete setting. So you start at some theta. You then do so these are fine-tuning steps. using your training data. You end up here. Some particularly fine-tuned set of parameters. You then evaluate. I'll use a different color for this, because that's not actually moving anywhere. You evaluate a test loss on that, and then you compute this. This is the derivative you want. How would this test loss have been different if your initialization for fine-tuning had been slightly different? Okay? So I want to make sure if you have a question about like just the basics of everything, you should ask it so that I can then go into how to think about it more. Yeah.
So is the only reason this is different from normal SGD because you're just doing it I times, and every I times you're letting the supervisor know?
Okay, great. So the question is, what's different about this from just doing regular SGD? Yeah. So that's a really good question. So let's understand a comparison of what does it mean to do regular SGD here. So one way you could do regular SGD, so maybe I'll write that out, right? So let's write out an alternative approach to make sure you can see the alternative approach. The alternative approach actually is not bad. Okay, so I'm going to write it over here. So the alternative approach, which can be done in some settings, would be this. So I'll call this just normal SGD. Okay? So just normal SGD would say, set your model up like this. Shared model. Okay, then go to a bunch of different task heads. Okay, a bunch of different task heads for your different tasks. These themselves, depending on the structure of your tasks, might themselves consist of like a hierarchical structure, where you say, like, okay, I have a bunch of tasks that are all kind of classification among four somewhat related things. So I'm going to share a linear layer among those four different things, and then I'll have like specific ones for each individual one as well. So anything you want to do, like use your engineering about the same way we had to use engineering about choosing a training loss specific to task, and things like this. We're just going to also use some similarity between tasks, okay, that you might know as a human being about those tasks. So put all that in. Then what you're going to do is just SGD on training examples across tasks. Okay, so what that means is you say, for example, you're going to you treat your training data set of data sets as instead being one big data set in which you have different losses attached to different examples. You just augment the y's with a categorization of what kind of thing is it. And then you have, in this example, you have different loss layers here. You have a bunch of different losses. And so you simply do them one task at a time. Not even one task, one example of one task at a time, and just keep doing updates. And what will happen is that the shared thing will keep getting gradients from everybody, from all these different tasks, and we'll be doing updates while these individual ones will be getting updates only from their specific task. But at the end of this, you're going to use the shared parts for doing fine-tuning on a test task that you might have at the end, something you actually want to do. Is that what you mean by what just doing SGD?
I'm not sure.
Okay, so the reason I drew this as an example just SGD is also because this is not a bad thing to do. This is actually a very reasonable thing to do. It's actually an ongoing topic of great discussion of whether this actually can outperform this approach in practice, perhaps with some twists added in. But so the reason I did this is that in this approach, there's one set of parameters, right, that are everything in this model. Think of this PyTorch thing, it's one set of parameters. When you do an SGD step, every parameter updates. Has a gradient, okay? Over here, in the mammal drawing, these fine-tuning steps that correspond to B, step B, these are tentative updates. Okay? They're just tentative updates. They're exploratory updates. They're like, let me see what happens if I were to fine-tune this model. But I'm not committing to these steps at all. I'm just wanting to say, okay, this is what I'd like to do. Then I end up somewhere. This is a tentatively updated state of the model. Then I evaluate the loss on that. Having evaluated the loss on that, I can then compute the gradient of this thing, this loss, with respect to where I started. So the derivative here is very different than the derivative here. So the derivative here you would do for just doing SGD would be on the loss with respect to the parameters of the system. So of course, the derivative of this loss with respect to parameters here is 0. It doesn't change. So it will not do a gradient update on these things. But the derivative of this loss with respect to parameters here in the shared model might be something, and you'll take a step in that direction. Okay, yeah.
Is there any notion of a batch size for this new SGD, or do you just pick one task to do at a time?
Okay, great question. The question was, hey, we have to think about batch sizes. Like, what would be a batch size here, right? And so the answer is, we'll talk more about this in a bit, about the issue of batches. In principle, at the high level, you could do a batch, right? You could do a batch of different tasks, fine-tune all of them in parallel, right? So what that means is you actually take this as the initial condition for many such tasks, and then have different steps for all of them. Then they'll all diverge off. They'll all go in their own different directions, potentially. Train them all. You get a bunch of different losses. Ask all of them, hey, how would you move the initial condition? Right? So you can use a batch here. In principle, that's totally fine. So there is a concept of batch size. We'll get more into details of batch sizes because of you'll see something from an implementation point of view that will force us to make batch size decisions. But it's a good question. Like the idea here in spirit, the first level idea is that literally do everything that you would have done for a normal SGD, except lift to the level of tasks. Where fine-tuning is just one of the parts of the operations. So, to be explicit, if you think of it that way, all of B, right, is just evaluating the performance of the model and its loss. Do you see that? This is like just one function from the perspective of PyTorch. It's like, compute the gradient of that function. This is the function. The function itself has steps inside of it, but that's okay. Yes?
I have a question that memo is more like an off policy update and the picture right is more like an on policy update?
Okay, so the question was, is there a connection between these ideas and the principle of, in RL settings, of whether you're operating on policy or off policy? Okay, so these are actually orthogonal ideas. They're different. Okay, they're not there's no necessary connection between them. Okay? So what's happening in this approach is you're just taking steps on the tasks as though they're all part of one big task. This is trying to account for the fact that you want to be in a position that lets you then get to a good thing. So I wouldn't say the comparison is to on policy or off policy in RL. If you want to, it's kind of a bit of a stretch. This has a bit of the feeling for people in certain RL context of like the idea of Bellman iterations, thinking about them, right? Is that you want to be in a good place so that you could be in the right place at the end when you get more information. So if you think about the general approach of dynamic programming as a way of doing solving stochastic MDPs, that says it's not just important to be in the greedy position. It's important to be in a position that then gives you the right place. So if that's what you're connecting to, is the idea that off-policy approaches take the Bellman operations more seriously, for example, like off-policy friendly things like Q-learning, right, as opposed to simply doing policy gradient. Again, this is for people who are thinking about RL. Then in that case, yes, there is that connection. But it's not really about off-policy and on-policy. It's about something more basic. Okay? Again, that's not in scope for this class because we're not taking RL in scope. Yeah?
So the parameters before they're fine-tuned, are they the same across the tasks? Like, are they the frozen model parameters, or what are they?
Great question. So let me go here and mark another alternative approach so we can answer your question. Because I want to make sure that folks who are not here can understand. So second alternative is just frozen model . Okay, so another approach would just be you have a model that you pre-trained in some way, and you're going to want to be able to do well in multitask learning. And so all you do is do each task treating the model as being completely frozen, right, with something that's task specific. So this approach, consider this like the 0th alternative. You never do any training based on the fact that you actually have a bunch of example tasks. All your training was done using some other thing. So what we're trying to do here, when we think about the parameters before part B, is we want to tune a model so that it will be good in the setting of being fine-tunable for your task. So it's kind of an interesting kind of hybrid thing. What this approach says is that we're not quite freezing this model completely. So during training, it's completely unfrozen. So during training, we're doing lots of updates on it. But at test time, what we're going to do is we're going to semi-freeze it, right? In the sense that it'll have a checkpoint. We'll restore to that checkpoint, and then we'll train on the task we have. And then we'll use it on that task. But when a new task comes, we'll restore back to that checkpoint and train it on that task. You see? So it's really, we're trying to learn a good initial condition for fine-tuning. So it's neither fully frozen, the way that we talked about, like if you had made this frozen model using some pre-training, using some self-supervised loss, nor is it that we expect to use it in a way that will keep adapting given different tasks as they come. It's kind of in between. It's trained across lots of tasks now to get a good initial condition, but then we'll do it on a task-specific way. Yeah, question?
The derivative of partial L test, partial zeta 0 seems extremely hard to solve.
Yeah, so, okay, that's the next topic I want to talk about. So the question is, I want to divide this question up into two parts. The question is this thing really hard to solve? And the answer is, it depends what you mean by hard. Okay? So if what you mean by hard, do you have to write a lot of code to do that and that code is hard to debug, okay, the answer is sort of no and sort of yes, okay? In that you can write it very simply, especially if you're using JAX. JAX makes it easier to write that code. But conceptually, it just says, hey, just compute a gradient from here to there, okay? So it depends on what you do. The problem is that if you do that, you'll write code that if you had access to infinite precision real valued computation, you would get the right answer. But in practice, if you just did what I said here, you would get a bunch of nans as your gradients. And then you're like, oh, okay, now what do I do? So I'll talk about why in a moment, right? Why that is the case. But conceptually, all of these steps are iterations. And there's nothing about an iteration that stops PyTorch from taking derivatives. There's no, so what stops a derivative, right? What stops a derivative is something like an argmax or an if statement, right? So you're right about that. So if the way that you would do fine tuning would involve a while something is something type of thing, then yeah, you might have a problem because that if the while something is like an if statement in there. Right? And taking a derivative through an if statement doesn't quite work quite right. But if you instead said, I'm going to fine tune using the following prescribed number of steps, right? Then there's no if statement. And there's nothing stopping a derivative. So whenever you have a prescribed number of steps, you can just unroll your loop. Right? So then you just have one big long block of code in Spirit. And that's fine. Right? You can take derivatives through it. Okay? But that's actually the topic I want to get to. Right? It's like let's draw this out. And then we'll see what we need to do. Okay, so I'm going to draw this in block diagrams for a moment. So I'm going to say I start with theta 0. Then I'm going to train. So here I'm going to make this precise, right? So I'm going to say, let's say k steps. So everything I'm drawing here, I'm drawing out all of this, right? Into just in diagram form. K steps of SGD. Then I'll get a theta tilde. Then I'll evaluate my loss. I'll out set. And then I get an average loss. So now you can see this is like everything just flowing in one direction. So you can take a derivative back. So training k steps of SGD, so this is like a loss layer. You see this? This is like a loss layer. And this is like a neural net. Okay? So, and these are the parameters of that neural net. So then let me expand this out. So what is it in terms of these little trained k steps of SGD? This is like this. Theta t plus 1 equals theta t plus eta inner. So inner is the learning rate for this. Inner learning rate. Oh, I guess I should use a gradient descent so I can do minus. And here I have a gradient of a training loss evaluated on theta t. So these are the updates. These are the gradient updates of k steps of SGD inside here. Now I could have weight decay if I wanted. Okay? So like a comment, could have weight decay too. Not a problem. So if I did that, I'd put a 1 minus something in front of on that. Okay, so this is so far this is fine. So this is what the iterations of k-steps of SGD look like. So we can unroll this loop, is what I was saying. Okay. So unroll loop. The SGD loop. So what happens is it looks like this. I have theta 0. Theta 0, maybe I'll give myself a little bit more room. Theta 0 then goes into something which computes the negative gradient of the training loss. So again, there's I'm going to suppress the dependencies. Also a training example that's coming in here. Okay, but I'm not taking a derivative with respect to it, so I'm not worried about it. Just coming in. Then this gives me this part. I'll take it and I'll multiply it by eta inner scalar, and that gives me this term, to which I will add the original theta 0, and now I have theta 1. And then I do this again. And then I have theta 2. Do you see it? See what's happening? So I keep doing this. Okay? Then I'll get theta, I don't know, capital T, some total number of iterations of this. And then this will then go into, this is theta T equals theta tilde. And this will then finally go into some loss test loss. And so then, having done this, this entire block here is the same as this. Does everyone see that? We're just unrolling it out. Now you can see that, what does this look like to you? Yeah, so you can see a ResNet type of thing, right? That's happening with the residual connections. And so this whole thing is basically like a deep RNN. Right, so this is deep. Okay, so like a deep network. That's fine. We know how to take gradients here. So again, we do this. So this is just so I can make it clear. Maybe I'll use the same notation. Did I say k steps? Oh, sorry. Instead of t, I'll just use k, because it said k steps. There's like a deep net. These are residual style connections. So the fact that these are residual style connections tells you something. It tells you that when you compute a gradient here, you're probably not scared of dying gradients. Right? You see that? Because you have residual connections. So the gradient will come back to the beginning. But what are you afraid of? Exploding gradients. Yeah. Because you're doing something over and over again, and you can definitely imagine these gradients can end up exploding on you as a result. The gradients to this, right? The question, the gradients to theta 0 that can explode on you. Okay, so don't fear dying gradients. But do fear exploding ones. So now is where you realize that you're a little stuck. Okay? If you try to do this, great. You're afraid of exploding gradients. When we talked about deep networks before, we said, okay, yeah, if you're afraid of exploding gradients in the context of something that's like a residual network, you can go in and put in some normalizations, right? But here you can't. Okay, do you see that? Because if you put in normalizations here, you're no longer reflecting what you think will happen at test time when you're fine-tuning anything. Do you all see that? So your go-to strategy for fighting the problem of exploding gradients is not available to you. So we're stuck with another more basic approach. The more basic approach is you have to dial the inner learning rate down. Because that's what's, remember, if this inner learning rate is 0, then there's no exploding gradient. Right? The exploding gradient is coming from this thing. So if this is small enough, you won't have an exploding gradient. Or you don't make it that deep. So practically, need to limit k and eta inner. Do you all see that? Like, you have to do this. So now you find yourself like, okay, wait, now what? What do we do? Right? Here now it's a little weird because we said we have a training data set of data sets. And if I limit my steps to k, then what does that mean? So there's a couple of things you could do. You could say, okay, that's forcing me to say that I have to. So remember, when you fine-tune a model using training data, what would you do? You would traditionally take it and say, let me train for. I'll shuffle my data. I'll put it into batches. I will then, based on what will fit in memory, then I will proceed to execute a set of epochs of training, right? Until I get good convergence and things to learn. All of this takes iterations. But here, iterations are a precious resource because you can't run this very long and then before your gradients stop working. So you can try to say, okay, I'll stuff bigger things into my batches. Right? So I'll take the training data set, that training task data that I have, and I'll put it into bigger batches so that I can get more done in one iteration. But again, you're going to come up with at some level, you're going to hit a memory constraint of how well you can make, how big you can make that batch. So in many problems, depending on if your data set is pretty large, you might not actually be able to practically go through all of your training data in k iterations. So you might say, okay, I'll live in one epoch. I won't even try to do multiple epochs. So I'll live in one epoch. So this is like a challenge, right, that we have to deal with. So what do you do about it? Let me pull this over here. Knowledge distillation. Okay, that was not planned, but I'm not going to use knowledge distillation to solve this problem. So I'll erase this. So practicalities. What you can basically do is, a key idea, is always the same key idea in deep learning. Do what you can, right? So So treat it like a data augmentation problem. So when you sample your task, make a random k-step version. Okay, just make a random k-step version of that task. So, you sample task 5. Task 5 has 1,000 things of training data associated to it. Well, you can't go through all 1,000 of those. Pick a subset, a new batch. Make a new batch. Size, whatever fits that you can do in k-steps, pick that, and then take a step along that direction. This will give you something. Now, it's still not satisfying. This approach is still not satisfying because you feel like you're not actually able to fully fine-tune this task. So you don't know what the initial condition effect would have been. Right? You just can't see it. So this approach is, it does something, but now you can begin to see why, practically speaking, mammal-style approaches with the necessary things that you have to do to make them work, they stop being as different from these approaches. You can't actually go and see how the entire thing would fine-tune necessarily. Okay? Because you can't do it. So another approach of what you can do has a clever name. Okay? So the clever name approach is reptile. Reptile strategy. Okay. So this picture is meant to illustrate something. I didn't draw this picture just arbitrarily. So when I drew this picture, what you're seeing is that actually for this task, these fine-tuning steps are all kind of pointing in a similar direction. So I drew this picture for a reason. So it could be that you think that, so when you ask for, so what is this saying? Okay? This is saying, what's the derivative of this loss with respect to this theta? Now, if these training points are like your held out test points, like, if you see this picture, predict, where's the next step going to be? Right? Think about it, it'll be somewhere here. You see that? It'll be pointing on the right side. Does everyone see that kind of just intuitively? So, this derivative, what it's asking is, I wish the initial point was different. How much different would I make it? And the answer is going to be, please be to the right. Right? Do you see that? Like it's kind of from the picture? So this turns out to actually happen quite a bit in real problems. And so people, the idea of the reptile strategy is that says, you know what? Instead of taking the derivative here, remember, it's the taking of the derivative here that's causing all the trouble. Right? Because executing this is fine. Like, executing this is no trouble at all. This is like evaluating a ResNet going forward. Things are not necessarily exploding in any way. But the gradients are what could explode coming back. So it says, what is the cheap way of doing a gradient without computing a gradient? And that is, the gradient is telling you where you should be, where you want to move. So one way of seeing where you want to move is to see, where did I move to? And presumably I wanted to move in that direction. You see that? Okay? So the reptile strategy says, in place of trying to compute this thing, right? Just use which way do I go? Oh, sorry, minus this, right? So this is like, when I do this, of course, why do I do this? Because now I can make K big. I can take lots of steps because it doesn't cost me anything. All I need to do is to make sure that my network is stable in training. But for the network by itself, I can put in all the normalization layers or whatever I want. So there's nothing wrong with training my network. The problem is when I did this unrolling, I'm not allowed to put any normalization layers in here. And that's what's causing me to have problems of exploding gradients. So this reptile strategy says simpler than taking a derivative is just to use this as the proxy. So what this means is we take, i.e., we update using some learning rate times, I'll use t for something bigger. So the picture for reptile looks like this. You start here, right? And then you take many, 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 many steps. Okay? Because the whole point, you can take more steps now. Then you say, great, what I want to do is to move in this direction. I will take a small step in that direction. And if, in fact, the dominant term pulling this here would have just been moved to the right, this is also going to move you to the right. Does everyone see that? So this is another way of getting around the problem of having to do these updates and compute these derivatives. Well, I'll just like not compute the derivative. Yeah.
So I mean, I can see the explanation, but like on the left, I see something like it's like kind of an Asian-like, right? And there we have like, I don't know, it's like SGD, right?
Yeah, it's a great question. So let's come back over here and say, in this, these were computed by PyTorch, right? So PyTorch computed some first derivatives. And it did that. So it computed a bunch of first derivatives. Then you asked for the derivative of the final loss with respect to the initial condition. So you have to go back and run derivative operations back through here, which means you'll end up taking a derivative of a derivative. Right? So you'll have a second derivative term that's coming in. Now, the key thing, so traditionally, I'm going to answer your question kind of in a long way. So the key thing that we said at the beginning of class is that traditional second-order methods that would look at the full Hessian are intractable when you have lots and lots of parameters because the size of your Hessian is enormous. This avoids ever computing the entire Hessian because what it does is when it asks for the second derivative of this, it asks for the second derivative of this of this training loss, it's asking for the derivative of this gradient in a particular direction. And that's cheaper. So it never has to compute the whole Hessian, which is why this is actually tractable at all. So, but it is interesting that this doing this thing is actually like using second derivative information to do it, fundamentally. Because it's asking for how would I have liked, based on the derivatives I saw, how would I have liked the input to change? That's actually a second derivative. So this is fundamentally a second derivative type of object. But it's computable because of the way that we do it. Now, it is an interesting thing, right, that here we didn't compute the second derivative at all in the reptile strategy. You're just saying, I'm going to use this first derivative as the kind of approximation for it. That's true. Right? So you're asking, well, how can this possibly work? And the answer is, well, it works in exactly those cases when basically these entire sets of training steps actually had the dominant term of interest was actually a kind of drift, moving in a particular direction. Because if that's true, then you are going to pick that up. So what it's saying is that when you computed this thing that felt like a second derivative, actually the dominant part of it was very first derivative-like.
So are those like the biggest eigenvector of the Hessian? I don't understand like the biggest what you mean.
Yeah. Okay, so you're asking the question, is this related to where there are large eigenvectors in the Hessian? I believe the answer is yes, but I don't know it precisely, so maybe we can talk about it more in office hours. Right? We can try to work it out a little bit. I did want to connect a little bit to, in this the third strategy I'm going to describe for how you might deal with this is actually taking into account a little bit of the eigenvector perspective as well. So the final strategy that you can have to kind of deal with this problem. So again, I'm giving you a crash course at Mount. You can go read many, many, many papers about this. Says, hey, maybe what I want to do is take advantage of the fact that my task-specific heads that I have. So if I was in this frozen model case, then these task heads might be very easy to train. Because if I was in a frozen model case and I'm training a task head, for example, for a squared error loss, then all I'm doing is I'm treating this model as a black box feature generator. Those features I'm going to run through a least squares. But least squares, I have a closed form expression for least squares. So I don't have to solve it by doing iterations of gradient descent. So remember, the whole point is training k steps of SGD was our approximation for fine-tune it. So what if I fine-tune it in this style? In the style of having the model be frozen. Okay? So now we're asking a slightly different question. We're saying, instead of trying to get a good fine-tunable model, let me try to get a good frozen model. Do you see this slight distinction? So I'm going to just go for a frozen model instead as a way to think about it. So if I go for the frozen model strategy, then what would I do? Then what I can do is use a closed form expression for the solution of training with respect to a frozen model. But the great thing is a closed form expression, like, it looks like something like oops. Right, something like this. Right, this is like the solution to a ridge regression problem, right? So you have some regularizer, a bit of small regularizer. You do a phi transpose phi inverse phi transpose y, right? Where the inside of these phis, all of these, have outputs of quote frozen model. But this is differentiable. And so PyTorch can take a step through this. So same thing, right? You still have to have a held out test set. So it's like standard MAML, except instead of doing k steps of SGD, you use a closed form expression to solve it, or something like a closed form expression. This avoids having many, many steps. You still have the problem of make sure that this thing is stable for getting its gradients. So here you have an inverse, so you're always worried. But if you have something here that's going to prevent this from blowing up, then it should be fine. So then all you have to do is make sure this thing fits into memory, and for PyTorch to run the derivative up. You still might have an issue. If you have lots of training data, this whole thing won't fit. Right? But you might get a much bigger size of batch. So this can help you. So this kind of thing is, it has like lots of names. There's like a paper I can post on Ed, the thing. Something called Anil. Also one called R2D2. Funny names. That's related to this style. So I use the expression for doing it for like squared error, because that's the easiest one to think about. But actually the same strategy conceptually works if you can treat the final problem as a convex problem. So if the final problem is convex, for example, like logistic loss or cross entropy loss, similar things can be done. Remember, convex is like from your optimization classes, you know convex problems are like things that have closed form solutions, spiritually. So the same thing applies here. There's ways of taking advantage of better convex strategy approaches to find something you can differentiate that doesn't have to involve the same number of steps of SGD. So these are all different strategies that we can do for meta-learning. Now, why do they work? Right? The reason they work is that what they're trying to do is they're trying to say, hey, I want to have something where, like, what would make this succeed? Like, what would make a few steps of SGD succeed? What would make a few steps of SGD succeed is if the gradients were such that they were pointing only very strongly in only a few directions. And those few directions were such that you could then do well in your task. So what this is doing is all of this is adding pressure to train the model to have strong gradients in a few directions which are task relevant. So if you start off with something which is very not tied, this is basically asking this loss, you do better with this when the model is a purifying model of pulling out the right things for the task. Okay, all of these will do better that way. So even here, remember when we computed the derivative features in the context of what gradient descent sees, you saw that whenever you have a linear layer or something on top, the derivative features associated with that are actually the output of the shared model. So both of these have some set of features that are actually in common. There's more features here that come from in here. So this is like the bigger picture of what's happening. So in the homework, we've given you a problem that's like the super simplest one where you can visualize everything. And we should try to show you why it is that these steps actually work in expectation. As well as that you see on a very simple model where you can see what's happening. That how you'll watch how meta-learning will cause the learned model to start purifying the relevant features and make them visible to you. Okay? So this is meta-learning. Now, again, final comment I wanted to make is, in practice, all of these fancy approaches are competing against this approach. And in this approach, you also have the idea of if you can find relevant data to come up with a self-supervised surrogate task, you can train that also. And so that tends to be quite effective. And so it turns out that in practice, the advantages of doing this is, again, generically, for generic problems, is less as compared to simply doing this strategy, or even this strategy, if you have enough data. But in specific contexts, if you're working in a particular domain where you do not have access to gobs and gobs of generic data, then these approaches pay off quite a bit. Mammal-style approaches pay off quite a bit. Okay, with that, I wanted to sort of leave fine-tuning behind and switch gears to talk about models for generation, which is what I wanted to make sure you all, by the end of the class, hopefully understand how the kind of spirit behind what makes things like these diffusion models for image generation work, as well as what makes like ChatGPT work beyond what we've already been taught. So that's my next goal. See if we can achieve it. I don't know if we will, but we'll try. Okay, so before I spend time on that, any questions on this? Yeah.
One more question. If we are facing the frozen model, then what we are going to update using the capture.
Great question. So when I say this, what I mean is that I would like to train a model that I expect to freeze. Okay? So I'm training a model, and then I'm going to freeze it. But right now, I'm training it. Okay? When I use it on a new task, I'll treat it as though it's frozen. So that's the strategy that I'm trying to do here. Of course, you can combine things. The important thing is I'm trying to give you here are like principal directions that you can move in. You can combine them. Right? So if you say that, no, but I don't want to freeze it. I don't really want to freeze it. This will say, okay, you don't want to freeze it, but remember, because we told you before, the tangent features associated with this are the outputs of this model. So they're always going to be relevant. So even if you want to train this too, getting this right is good. Remember we said before about when you want to actually do fine-tuning, you want to actually do fine-tuning by first getting your head trained on the frozen model, on the model as though it were frozen, and then do the updates to prevent kind of forgetting happening on important directions here. There's an alternative approach I should mention in lecture. An alternative approach which is better than random initialization is zero initialization. So if you initialize to 0, then you're at least not going to send garbage back. You'll send zeros back. You'll first adjust those. But it's still not as good as actually getting this to something that actually works with the frozen model. So if you want to do a combination, you can do some training steps like this, trying to enhance the frozen aspect of the model. You can also combine it with straight mammal. You can also combine it with some reptile. But remember, what reptile is doing is saying, is there a long-term drift that's relevant here? Let's make sure we get that right. This is also, in a sense, trying to get that. Okay? And this is trying to say, hey, maybe we can do more of a local agility purification of things that are the actual tangent features here of the larger model. So you can combine them. Okay. Any other questions on this? Great. So now let's switch gears. We have 10 minutes. We can start. Oh, wow. I guess I should have expected this. So what we're interested in now is a different question than like classification or regression or unsupervised learning in the sense of clustering. we're interested in the problem of generation. Okay, this is dead. So this is sometimes also called simulation. So you've all seen examples of this, right, at this point, right? So this is where instead of the output being of your model being a label, right, from some conditional distribution. Okay, that's the goal. You want to be able to draw samples from something. That's how we formalize it, right? From a practical perspective, it's that, hey, I want to ask for something and get an example of that something. But how do we make that into something we can kind of reason about? We reason about it as the only kind of mental tool we have to get new things is drawing from a random probability distribution. Like mathematically, that's how we can like get something. Okay? So that's how we think of it as, drawing a sample from some distribution. When we ask for something, we can think of it as conditioning. So we want to draw from some conditional distribution, where the question is the condition. So before we can tackle this question, we have to start with make sure everyone's on the same page. So basic. How do we sample from a known distribution? So the problem we actually have is we want to draw synthesized examples from some conditional distribution where we don't have access to the distribution at all. All we have access to are examples. Right? That's the real problem. But before we can tackle that real problem, let's make sure everyone's on the same page. Suppose I told you I have a known distribution. Here's a known distribution. Draw me a sample from that distribution. How would you do it? So, someone raise your hands if you want to tell me how you draw a sample from a known distribution. Okay, so I'll start making it easier. So case one. A discrete distribution. Okay, so I have some discrete distribution. I give it to you. You have it. I would like to draw a sample from this. How would I do it? Yeah. I can use inverse CDF. Yeah, it's a standard approach. So inverse CDF style. So how do I do the inverse CDF style here explicitly? Tell me how to do it.
You just run the keyword and then you generate when you generate a random integer from 0 to whatever the total sum, and then you can binary search for whatever else you want.
Okay, I'm going to describe that with a bug correction put in just for the people. Yeah, that's basically the right answer. So the idea is start with continuous uniform random variable u. Then compare implicitly segment the unit interval as follows. 0, P1, P1 plus P2, P1 plus P2 plus Pn minus 1, and then 1. Okay, this is what you were saying, right? Does everyone see this? I just take these numbers that define my probability distribution, and I use them to cut the unit interval, right? And then C in which interval U lands and emit that. Okay, whatever that label is. Does everyone see that? So this is like a basic exercise from your probability course of how do you get random variables. You start with a uniform, and you can do it for discrete. It's pretty simple, right? You can tell basically each of these segments. So this segment has length P1. This segment has length P2. This segment has length P3, and this final segment has length Pn. All of them have length associated with the probability, and the whole point of a uniform random variable on the interval 0, 1 is that the probability of landing in an interval is proportional to its length. Right? Like that's literally why you construct uniforms. So this does it. Great. So case 2, continuous distribution. Right, some f of x. And so how would I sample from that? So I guess inverse CDF style. So just in the interest of time, we can just say it out loud. You take the distribution, the density, f of x, compute the CDF, and then use the sample of u to tell you where along the CDF to read the answer. It's the counterpart of this with infinitely many intervals. So what is the important lesson from here? The important lesson is if you want to do generation or synthesis, you have to have some kind of structure which acts like the distribution, learned distribution, and you have to use randomness. You can't draw samples without randomness. You need something to generate like a set of possible things to come out. How do you use randomness is like the name of the game. Okay, in everything here. How do you use randomness? So there's a bunch of approaches that are basically, you can think of as they're like in the spirit of the inverse CDF style, that they take random things and they run them through a function that should be like the inverse CDF and generate something that comes out. But there's another way to also sample from a known distribution that you might have heard about. And that's the only thing I want to comment on briefly. So another way of sampling from a known distribution is to set up some kind of random walk. And if you set up some kind of random walk whose stationary distribution is the distribution you're interested in, then you can sample from that distribution by taking a simulation run of the random walk and then seeing where you end up. This feels very direct. But the other approach is also interesting and useful. So when we talk about generation, when we talk about things like GANs and variational autoencoders, we'll be talking things that are roughly in this family. When we talk about diffusion models, they'll be in the other family. Okay, but we're going to use the same building blocks to understand everything. Okay, so that's where we're going next. Along the way, we are going to talk about using GPT to generate things, which is kind of an interesting in-between approach. Okay, So with that, I'll switch to office hours now, and then we'll continue on Friday.